Good morning to all. I am A.RAKINI, Assistant Professor of Chemistry, D.M. College for Women, Autonomous, Nagapattinam. Now I am going to present my topic on Nucleophilic Substitution Reactions. This topic present in 2nd MSc Chemistry, subject in Organic Chemistry. This is Unit 1 and then Module 1. Now I am going to the presentation overview. First of all, Aliphatic Nucleophilic Substitution. This type of SN1. SN1 means unimolecular nucleophilic substitution reaction, and then SN2. SN2 means bimolecular nucleophilic substitution reaction, and then SNI. SNI means intramolecular nucleophilic substitution reactions, and then neighboring group participation, allylic carbon and vinylic carbon, aromatic nucleophilic substitution, and this type of SN1, and then Benzyne mechanism. Let us see that aliphatic nucleophilic substitution. First of all, what is the substitution? Replacement of an atoms or group of atom by any other atom or group of atom. A reaction in which the functional group of one chemical compound is substituted by another group. What is the nucleophile? A reactant that provides a pair of electrons to form a covalent bond present. At least one of unshared pair of electron present and then Lewis space is present, attracted towards positively charged species may be neutral or negatively charged. Example for chlorine, bromine, iodine, cyanide, hydroxide, ammonia, primary amine, water molecule, and then extra. Introduction. A nucleophilic aliphatic substitution is a nucleophilic substitution reaction in which the ligand replaced by the nucleophile is bonded to a carbon atom that is neither a member of an aromatic ring nor a carbonyl carbon. An example of nucleophilic substitution is the hydrolysis of an alkyl bromide under basic condition where the attacking nucleophile is hydroxide and the leaving group is bromide. Nucleophilic substitution reaction are common in organic chemistry. Nucleophiles often attack a saturated aliphatic carbon, less often they may attack on aromatic or unsaturated carbon. SN1 mechanism. You know SN1 mechanism means unimolecular nucleophilic substitution reaction. SN1 mechanism, a carbocation is formed which is a planar and hence attack a nucleophile. This is a second step. May occur from either side to give a racemic product, but actually complete racemization does not take place. This is because the nucleophilic species attack the carbocation even before the halide ion has moved sufficiently away from the carbocation. The negatively charged halide ion slide the carbocation from being attack on the front side and back side attack, which leads to inversion of configuration. Thus the actual product no doubt consists of a mixture of enantiomers, but the enantiomer with the inverted configuration and complete racemization does not occur. This is mechanism. This is an example of a reaction taking place with a SN1 reaction mechanism is the hydrolysis of tertiary butyl bromide forming tertiary butanol, elimination of bromine and then hydronium ion. This is a SN1 reaction takes place in the 3 steps. First one is formation of a tertiary butyl carbocation by separation of a leaving group. This is a bromide anion from the carbon atom. This step is very slow step. Next one, second step is a nucleophilic attack. The carbocation react with the nucleophile if the nucleophile is a neutral molecule. It's a solvent. This third step is required to complete the reaction. When the solvent is water, the intermediate is a oxonium ion. This reaction step is very fast. And then third one is a deprotonation. Removal of a proton on the protonated nucleophile by water attacking as a base forming the alcohol and a hydronium ion. This step is very fast. Next one, this is The structure is a recombination of a carbocation. First of all, carbocation is a attack with a nucleophile. For example of a tertiary butyl carbocation attack with the water molecule to give the product of tertiary butanol and then hydronium ion. Next one, SN2 mechanism. You know SN2 mechanism? This is a bimolecular nucleophilic substitution reaction. The SN2 reaction is a type of reaction mechanism that is a common is organic chemistry. In this mechanism, one bond is broken and one bond is formed. This is a one step. SN2 is a kind of nucleophilic substitution reaction mechanism. Since two reacting species are involved in the slow rate determining step, the term substitution nucleophilic 5 molecular or SN2. The other major kind is SN1. Many other more specialized mechanism of substitution reactions. The reaction type is so common that it is here has other names. Example of bimolecular nucleophilic substitution are among inorganic chemists, and then associative substitution or interchanges mechanism. Then this structure is a ball and stick representation of the SN2 reaction of methanediol with methyl iodide yielding dimethyl sulfonium. Note that the attacking group attacks from the backside of a leaving group. And then this is reaction mechanism. The reaction most often occur at the aliphatic sp3 carbon center with an electronegative stable leaving group attached to it, often denoted it is a X, which is frequently a halide atom. The breaking of the CX, X means halide bond, and the formation of the new bond, often denoted CY or a CNU, NU means nucleophile, occur simultaneously through the transition state in which a carbon under nucleophilic attack is a benda coordinate and approximately sp2 hybridized. The nucleophile attack the carbon at 180 degree to the leaving group. Since this provides the best overlap between the nucleophiles lone pair and the CX sigma star antibonding orbital. Next then, the leaving group is the booster of the opposite side and the product is formed with inversion of tetrahedral geometry at the center atom. If the substrate under nucleophilic attack is chiral, then this often leads to inversion of configuration. This is stereochemistry. It is also called as a Walden inversion. In an example of SN2 reaction, the attack of bromine is the nucleophile. On the ethyl chloride, the electrophile result in ethyl bromide with the chloride ejected as the leaving group. This structure, this is the reaction of SN2 reaction of chloroethane and bromide ion. If the molecule that is undergoing SN2 reaction has a chiral center, then it is possible that the optical activity of the product would be different from the of the reactant. In the example of 1-bromo 1-fluoroethane can be undergo SN2 reaction to for 1-fluoroethane 1-ol with the nucleophile being a hydroxide group. In this case, if the reactant is levorotatory, then the product would be a dextrorotatory and then vice versa. This structure of SN2 mechanism of 1-bromo 1-fluoroethane with one of the carbon atom being a chiral center. This is SNI mechanism. SNI or this is substitution nucleophilic intramolecular reactions also. They stand for the specific but not often encountered nucleophilic aliphatic substitution reaction mechanism. And the nucleophilic reaction which occur with the retention of configuration, but later was employed to various reaction that proceed with a similar mechanism. A typical representation organic reaction displaying this mechanism is the chlorination of alcohol with the dionyl chloride or the decomposition of alkyl chloroformate. The main feature is retention of stereochemical configuration. Dionyl chloride first react with the alcohol to form an alkyl chlorosulfate, actually forming an intimate ion pair. The second step is the concerned loss of sulfur dioxide molecule, and it is a replacement by the chloride which the attached to the sulfate group. And the difference between SN1 and SNI is actually that the ion pair is not completely dissociated, and therefore no real carbocation is formed, which would lead to a racemation. This reaction type is linked to many forms of neighboring group participation. For instance, for the reaction of the sulfur or nitrogen lone pair in sulfur or nitrogen to form the cationic intermediate. The reaction mechanism is supported by the observation that addition of pyridine to the reaction to inversion. The reasoning behind this binding is that the pyridine react with the intermediate sulfate replacing chlorine. In the complete picture for the reaction, the sulfate react with the chlorine ion in a standard SN2 reaction with the inversion of configuration. When the solvent is also a nucleophile, such as a dioxin 2 successive SN2 reaction take place, and the stereochemistry is again retention. With the standard SN1 reaction condition, the reaction outcome is retention via a competing SNI mechanism and not a racemation, and the pyridine order to the result is again inversion. Next one, going to the neighboring group participation. What is the neighboring group participation? In organic chemistry, neighboring group participation is defined by the International Union of Pure and Applied Chemistry as a interaction of a reaction center with a lone pair of electrons in an atom, or the electron present in a pi bond containing within the parent molecule but not conjugated with the reaction center. When neighboring group participation is in operation with the normal for the reaction rate to the increased, it is also possible for the stereochemistry of the reaction to be abnormal. It is unaccepted with compared with a normal reaction. While it is possible for neighboring group to influence many reaction in organic chemistry, example for the reaction of diene such as 1,3-cyclohexadiene with malic anhydride normally gives the N2 isomer because of a secondary effect, overlap of a carbonyl group and then bi-orbital with the transition state in the disorder reaction. This page is limited to neighboring group effects in the carbocation and SN2 reactions. Neighboring group participation by heteroatom lone pairs. In this type of substitution reaction, one group of the substrate participates initially in the reaction, thereby affects the reaction. Due to neighboring group participation, the reaction rate gets increased by many folds. A classical example of neighboring group participation is the reaction of sulfur or nitrogen with a nucleophile. The rate of reaction is much higher for the sulfur mustard and the nucleophile, and then it would be for a primary and secondary alkyl chloride without a heteroatom. Neighboring group participation by a cyclopropane, cyclobutane or a homoallyl group. In cyclopropyl methyl chloride is reacted with ethanol and water, then a mixture of 48% of cyclopropyl methyl alcohol and then 47% of cyclobutanol and 5% of homoallyl alcohol, it is a but3-enol is obtained. This is because the carbocationic intermediate is delocalized onto many different carbons through a reversible ring opening. Neighboring group participation by an aromatic ring. In the case of benzyl halide, the reactivity is higher because the SN2 transition state enjoy a similar overlap effect to that in the allyl system according to the molecular orbital theory. An aromatic ring can assist in the formation of a carbocationic intermediate called as phenonium ion by delocalized the positively charged allylic. Next one, the allylic carbon. It is a very important carbons on allylic rearrangement or allylic shift is an organic reaction in which the double bond in an allyl chemical compound shifts to the next carbon atom. It is encountered in nucleophilic substitution. The reaction condition that favor a lesser known reaction mechanism. The intermediate is a carbocation for which several resonance structure are possible. This explanation explain that a product distribution or a product split after recombination with the nucleophile. Why? This type of process is called an SN1 substitution. Alternatively, it is possible for nucleophile to attack directly at the alkyl position, displacing the leaving group in a single step in a process referred to as SN2 substitution. This is likely in cases when the allyl compound is unhinged and a strong nucleophile is used. The products will be similar to those seen with the SN1 substitution. Thus, reaction of 1-chloro-2-butane with the sodium hydroxide gives a mixture of 3-butane-1-ol and 3-butane-2-ol. Nevertheless, the product in which the hydroxide group is on the primary atom is mirror. In the substitution of 1-chloro-3-methyl-2-butane, the secondary 2-methyl-3-butane-2-ol is produced in a yield of 85%, while that for the primary 3-methyl-2-butane-1-ol is 15%. In the reaction mechanism, the nucleophile attack not directly at the nucleophilic site but in a conjugated addition over the double bond. In the first step of the macrocyclization, and the diol group is one end of 1-by-bending diol react with the butadiene diol is 1 to the enone, 2 is 2 in an allyl shift with the sulfone leaving group, which react further with the other end of the conjugate addition reaction. In this reaction sequence, a Jacobson epoxidation add to a epoxy group to a tie-in with serves as the leaving group reaction with the pyrosyl nucleophile. And the second nucleophile is methyl magnesium bromide to the pyrosyl group. Next one, the vinylic carbon. And the vinylic carbon is a carbocation with the positive charge on an alkene carbon. It is the empirical formula is C2H3+. More generally, a vinylic carbon is any disubstituted trivalent carbon where the carbon pairing the positive charge is part of a double bond and is a sp hybridized. In the chemical literature, substituted vinylic carbon are often referred to as vinyl cations and understood to refer to the class rather than the C2H5+ variant alone. In the vinyl cation is one of the main type of reactive intermediates involving a non-tetrahedrally coordinated carbon atom and is here necessary to explain the wide variety of observed reactivity trends. Vinyl carbons are observed as reactive intermediates in solvolysis reaction as well as storing the electrophilic addition to alkynes, for example through protonation of the alkyne by a strong acid. As expected from this sp2 hybridization, the vinylic cation refer a linear geometry. The compounds reacted to the vinylic cation include allylic carbocations and benzylic carbocations as well as aryl carbocations. Compared to other reactive intermediate such as radical and carbanion, and the vinylic cation long remained poorly understood and they were initially thought to the too high energy to form as reactive intermediates. Vinylic cations were first proposed in 1944 as a reactive intermediate for the acid hydrolysis, acid catalyzed hydrolysis of alkoxy-acetylene to give alkyl acetate. In the first step, that facile hydrogen hydration reaction, which was the rate limiting step, a vinylic cation reactive intermediate was proposed. The positively charged was played to formally on the ti-coordinate carbon. This is a first time such a transition state can be found to the literature. Vinyl cations have been observed as a reactive intermediates during solvolysis reactions considered with SN1 chemistry, and thus these reactions follow first order kinetics. Generally, vinyl halides are unreactive in solution. The silver nitrate does not precipitate silver halides in the presence of vinyl halides. Cationic species. The introduction of super leaving group in the 1970s first allowed for the generation of vinylic cation reactive intermediates with lifetimes. These excellent leaving groups such as trifluoromethane sulfonate and fluorobutane sulfonate are highly prone to SN1 reactivity. Utilization of these super leaving groups allowed researchers for the first time to move beyond about the extension of such vinyl cations. Note that unlike the allylic and benzylic carbocations top left and right respectively, the electron deficient carbon of the vinyl carbocation, it's a bottom, is double bonded. The structure of the vinyl cation formation through carbon halogen bond cleavage. Next one going to the aromatic nucleophilic substitution. This is the aromatic nucleophilic substitution is a substitution reaction in organic chemistry in which the nucleophile displacing a good leaving group such as halide on an aromatic ring. Aromatic rings are usually nucleophilic, but some aromatic compounds to undergo nucleophilic substitution. Just as normally a nucleophile alkene can be made to undergo conjugate substitution if they carry electron withdrawing substitution. So normally nucleophilic aromatic ring also become electrophilic if they have the right substitutions. Next one, SN1 mechanism. This is also called unimolecular nucleophilic substitution reaction, but they used the substitution of only the aromatic. So it is called aromatic nucleophilic substitution. In this very rare mechanism, in aromatic compound, and it is observed in the benzene diazonium compounds. As you know, it is a two-step mechanism and the rate is independent of the nucleophile. The reaction of by elimination of nitrogen gives aryl cation attached to the nucleophile gives a substituted product. The aromatic SN1 mechanism encountered with diazonium salt. Example of nucleophile is a chlorine. It gives chlorine substituted product. Next one going to the benzyne mechanism. It is also known as SNEA mechanism. As elimination and addition reaction occurs. SNEA mechanism as elimination and addition reaction occur. It would not be easy to remove the chloride group from the ring due to conjugation between lone pair of electron of chloride atom and carbon atom in the ring. It was possible in SNAR mechanism due to presence of strong withdrawing group. So here the adjacent hydrogen atom in the ring is used for the reaction. This is the example of the chlorobenzene. The chlorobenzene react with the sodium amide and the liquid ammonia to give the benzene. It is one of the transition step, and then further up to give the product of ortho and meta aniline group. Here the very used of the, here we are using C14 means carbon 14 radioactive isotope of carbon. This is give the two product are produced here. One is directly or this ipso substituted product and the other is sign substituted product. Product means direct on the same position and sign adjacent position. It is here ipso means at the same position. Sign means at the adjacent atom position. Position means 2 and 6. Thank you.